before. Some people have talked about systematics. I will now put this together on. I'm still trying to find the right angle. So I will specifically talk about how to combine the different measurements that we will be able to do with LSST, why systematics are a particular challenge for that, but also how then doing point analysis can help us tackle systematics in the end. But to get started, here is a previous working model of cosmology that definitely was maybe 10, 20 years ago. And some of you might still try to do this today with Planck and DS data, where we went from photons to cosmology basically in a two-step process. There was the survey collaboration, operating the telescopes, doing data reduction, and then they released maps, catalogs, and value-added products, such as correlation function measurements or power spectra. Then some independent theorist comes along who sees all that happens in a survey collaboration as basically a black box, but has their code that connects theory to these value-added products and spits out parameter contours. However, as we embark on LSST data, the statistical power of this data set will be so fantastic that we have to abandon this old model of doing cosmology. Instead, we need big survey collaborations like energy science collaboration to carry out this whole step, all the steps going from photons to cosmology. So meaning if somebody wants to work on inference codes and determine cosmology parameters, they better talk to others working in the same collaboration who study foreground removal, star galaxy classification, galaxy shape estimation, photometric calibration, and so on, and vice versa. People working on these very pixel level techniques should absolutely be talking to the cosmologists developing new models over lunch break and figure out what theorists are interested in and where they might want to tweak their algorithms. So there should not be any black box anymore. That said, when we all talk to each other, we're still playing this game of connecting a cosmological model and parameters at the end to a galaxy distribution like that. So likely we will generate initial conditions, evolve them to get the dark matter distribution, then in comes the magic that is astrophysics. And then we want to compare our simulated catalogs to the sky. If we are as smart and futuristic thinking as some theorists like Marco, you can think about doing this comparison on the field level. But at least for now, in LSST, we are thinking about this in a slightly less massive data science challenge way. Namely, we will want to reduce the galaxy distribution observed by LSST into summary statistics. Of course, one of our favorite quantities in cosmology is the galaxy power spectrum. So the natural thing to start with is two-point correlation functions. So that's the axis probability of galaxy pairs over random distribution as a function of separation. And then if we have approximate distances to galaxies and understand galaxy bias, that's the relation between dark matter and light, then this two-point correlation function is just related by a simple Fourier transform to the matter power spectrum. And that then tells you that over here on very large physical scales, the amplitude changes as a function of redshift from redshift 2 to today through linear growth. Then here on intermediate scales, these wiggles, that's the BEO feature encoded in the power spectrum. And over here is all the information content in nonlinear structure information. In addition to this galaxy pair measurement, we will go and count overdensities. So that is massive galaxy clusters, as discussed in Tom and Mariana's talks. And then, if you want to be more ambitious, we can plan to do cosmology with voids, as we just heard before coffee break. And then if you want to be really futuristic in a summary statistics sense, we could go out and measure triangles of galaxies, which will probably keep us busy until the 2030s. And then in addition to galaxy positions, we will also use the shapes of galaxies. So that is weak lensing, which you already heard about in several talks and summarized nicely by Chiwei. So I'll just briefly mention here for the context of systematics again. We are looking at the deflection of the shapes of background galaxies by tidal structure. And that then leads to this nice tidal alignment of galaxies with overdensities. However, in reality, of course, background galaxies are neither perfect circles, nor are they these high contrast cyan objects against a differently colored background. Instead, we're doing this with maybe signal turning to noise fuzzy blobs, and we need to measure the shapes of those, which will, of course, not be a systematic tree measurement. And then the background galaxies may also not be randomly oriented. So you can see from that shape measurements and the intrinsic distribution of galaxy shapes will be key systematic uncertainties here. And then in practice, basically, we go out and measure the shapes of hundreds of neighboring galaxies to get a local estimate of this weak lensing shear. If that sounds like magic, we're lucky that nature built in a consistency check. That is, we can observe the same weak lensing effect, but using a completely orthogonal method. And that is weak lensing of the CMB. For that, we rely on the fact that the initial temperature field is a Gaussian random field, which then gets remapped by the large-scale structure between us and the CMB, and that causes a deviation from the Gaussian statistics. So we can use the higher order correlations of the temperature field and polarization to infer the matter between us and the CMB, and then compare that to galaxy-based weak lensing. But basically no correlated systematics. So that's the different types of measurements we want to do. And then we want to turn it into the best cosmology possible. As you know from plots like these that combine supernovae, the CMB, and BEO, multiple measurements will give, or multiple cosmology probes will at the end lead to the tightest parameter constraints. And in this nice case of uncorrelated probes, any theorist out there can basically take the posteriors from the individual calibrations, multiply them, and get this nice joint constraint. However, especially in the LSST context, when we talk about weak lensing, galaxy clusters, and galaxy clustering, that means that we measure the matter density field through 3 different ways. And we certainly don't want to overcount information. Also, these measurements all come from the same telescope, so they will share observation systematics, and some of them will be affected by the same astrophysics. That means we can't simply multiply posteriors, but need to do a full-on joint analysis. And I think this might be pretty much my only equation. The other one is a version of this, so bear with me, please. This summarizes already quite a few of the questions that we are asking more on the theory side in LSST right now. That is the question of how to constrain our cosmology parameters and what they can be, given our ability to model data. And then how to do this inference process. So first of all, we start with what parameter space are we going to analyze? Are we talking about WCDM or modified gravity? Like Tessa introduced the different possibilities yesterday. Then we have to decide for which data can we actually model these cosmology scenarios. Are we talking linear scales only? Can we include cluster number counts and so on? We might put in cosmology priors. Then we need a likelihood function, which for now we typically assume to be a multivariate Gaussian for 2-point statistics and maybe Poisson statistic for galaxy clusters. But it's clear that this approximation will not be sufficient for the LSST era. So that's one active area of work. Then here's our measured data vector again. We need a model for it that includes all our cosmology parameters and systematic effects. And these systematic effects, of course, then need to be consistently parameterized across all the different observables. And that will be one of our major modeling changes on that front. Then we need a joint covariance for this massive data vector. So this will be a very high dimensional matrix that's likely not sparse. And that we'll probably not be able to estimate from simulations. So that requires a lot of new statistical techniques. And then the focus of this talk, nuisance parameters. I've just listed them here in terms of the model. We will also need priors. And the important thing to keep in mind throughout this talk is that most likely our systematic parameters will far outnumber our cosmology parameters. And I should emphasize again that each of these boxes is the work of many people in LSST and outside. So I'm sorry if I'm just glancing over your area of work here, or if I later marginalize over the astrophysics that you're most interested in. But with this framework in mind, let's get ready for precision cosmology. Let's start with a series point of view here, where we still have the bullseye in the parameter space, so we know what we want. And we're in the era where our scatter is still large, so we might be doing all right or not. And then we get better data and apply our same techniques to these larger data sets. And then we might end up in a situation like this. So clearly, precision is not enough. Instead, what we actually need is precision and accuracy. So as our survey size improves, we also need to build more complex analyses so that we can actually use the shrinking error bar to still end up basically on the bullseye. That brings us to mathematics slightly, because as I said, the cosmology parameters is probably, that's a well-known parameter space, but what we now need is astrophysics and observational effects. This is just basically following from having excellent statistics. That basically means that we are person power limited, people in LSST and what systematics they can dream up to study right now. We did a simple experiment for this in DES. I think in 2013 we questioned all the working groups what systematics they're most worried about. And I would say the responses were not surprising. People studying cosmology from Galaxies said that we need to understand the galaxy luminosity function, galaxy bias through the nonlinear regime. Then for clusters, we need to understand the mass-observer relation. So how our observed clusters relate to the actual dark matter mass functions. The mean relation, scatter inlet, projection effects. Then for weak lensing, we need to understand how accurately we actually measure galaxy shapes and whether there's biases in that. We need to have a good model for intrinsic alignments and photometric redshifts. And then if you sum it all up, we got to a list of 500 to 1,000 parameters. And yeah, I think we can all agree that probably our baseline cosmology model will have less than 10 parameters. So that's already an interesting situation to be in. Meaning that our task from now on is to prioritize and marginalize. Of course, we can run with such a big model that would take forever. And if we're too far in our systematics budget, we might also lose a lot of constraining power. So we want to get this right. Fortunately for now, the statistical power isn't that great yet, meaning that we have a good training ground for getting ready for systematics limited cosmology. Specifically, today I will talk analysis, which analyzes 1,300 square degrees with about 7 galaxies, 7 source galaxies per square arc minute. And that's here in the context of previous and future surveys. By survey completion, of course, don't give too much about dates in the future. It's usually further away than it seems. And you can see how we went from this first series cosmic shear survey, CFHCS, to now surveys of a few thousand square degrees, but slightly different survey strategies. So if dark energy is more important at early times, then focusing on a smaller area but going deeper, like HSC, is a more strategy. Otherwise, focusing on the larger area and serving the weak lensing effect and everything below redshift 1 might be more promising. It's out how we will do. And that all is in training ground to deal with billions of galaxies that are in the 2020s. So the cosmology contours and the work leading up to it that I'll show now are thanks to the dark energy survey collaboration. This is probably a bit over 100 people that were still awake and smiling enough to make it to the picture at our collaboration meeting last summer, right before unblinding. I should say that right now there are around 400 people on our mailing lists. Many have phased in and out over the last 10 years, so this is truly a team effort of well over 500 people. And a broad range of experience. So as we're doing this within the collaboration. This is already cosmology without the black box. This includes experience from building the camera to modeling modified gravity. But on from people to galaxies. For year 1 analysis, we had 2 different galaxy samples, namely one of about 600,000 red magic galaxies. These are red sequence galaxies that lead to good or accurate photometric redshifts. And we use those for galaxy clustering measurements and as lenses for galaxy-galaxy lensing. And then we have another catalog of about 26 million source galaxies. So these can be fainter. These are the faint fuzzy blobs for which we measure galaxy shapes. And those are used in the cosmic shear analysis and as the source galaxies for galaxy-galaxy lensing. So meaning that we want to basically study the evolved matter density field below redshift 1 through the autocorrelation of these galaxy positions in tomography bins, galaxy clustering, through the correlation of galaxy shapes, so cosmic shear, and the cross-correlation between these 2 catalogs. And I should mention that doing cosmology with 26 million galaxies, that's quite an increase compared to previous analyses. So we are approaching precision cosmology for that. And in order to do this data quality justice, we attempted to do basically all the systematics limited parts of the analysis in 2 different implementations, starting with galaxy shape measurements, for which we rely on 2 very different methods. Let's start with IM3 shape, traditional shape measurement code that relies on fitting a Balchon disk template to each fuzzy blob and then estimating the ellipticity. This uses R-band data only, and leaves us with about 18 million galaxies for the cosmology analysis. And then we are lucky to have a very new shape measurement implemented for DES. This is meta-calibration developed by Eric Huff and collaborators and implemented for our data by Aaron Sheldon. And this estimator relies on deconvolving the telescope PSF, applying an artificial additional shear on each galaxy, reconvolving, and measuring the response of each galaxy to this additional shear field. This has the advantage that we don't need to assume that the galaxy is well fit by a Balchon disk model. It works for any shape. You can measure the stretching of any shape, and you can do it in multiple bands. So using GR and I band together, we end up with a galaxy sample of 26 million galaxies for cosmology. And then we do each analysis using both shear catalogs to make sure that our results are robust for galaxy shapes. Then, in addition to that, we have 2 independent calibrations of photometric shifts, where I show the baseline histograms over here. So our baseline estimate of the galaxy redshift distribution comes from the one black box in DS, I would say. That is a template fitting algorithm called BPZ, that spits out redshift distributions that look like the dashed lines in this plot. And then we calibrate this template fitted photo Z distribution using 2 different techniques. One is that we use the Cosmos catalog, which has 30 optical bands, so much more accurate photo Zs than DES. And we match DES galaxies to Cosmos and then resample the Cosmos redshift distribution. That's shown as the lines with the large statistical uncertainty in this plot. And then we can also use the fact that galaxy clustering maximal on small scales. So we cross-correlate this source sample with more uncertain redshift distribution with a well redshifts and check how big the clustering signal is. That lets us also infer the true redshift distribution or separation between these 2 galaxy samples. And from this cross-clustering technique, we then get these dotted symbols here with the error bar estimates. And for our key cosmology analysis, we use make sure that we get that our result is robust for these different redshift distribution shapes. With these inputs, now again, we want to go figure out our cosmology constraints. I've just told you about the basic measurement. So we end up with our data vector here. That is the cosmic shear, galaxy clustering, galaxy lensing correlation functions. And what's left for us to do is to implement an accurate model data vector, including the relevant systematics. We need a covariance, and we need to make sure that we sample this enormous likelihood correctly. Today, for cosmology in a systematic limit regime, I will focus on the first aspect, the model data vector, where we need to make sure that our systematics parameterization is sufficient for year one. But the first step, of course, is that we get the baseline theory right. So this is something that we internally knew as basically within DES we developed two independent likelihood pipelines, and then we started talking to each other. And the initial comparisons were interesting. We definitely had more than 20% agreement in some parts. That followed 2 years of way too many Slack messages. And Josons, who did this with me, claims that he lost his hair over this process. I can definitely say that thanks to DES year one, I don't get carded anymore. So this was quite an effort. But at the end, our two pipelines, shown here first of all the expected signal in the two shear correlation functions, galaxy-galaxy lensing and clustering. Then over here in red, the residual compared to the statistical error bar. These agree very well. So we can now say that the theory implementation and all the numerical shortcuts that we take to evaluate the correlation functions in finite time, these are a significant contribution to our error budget. Doing this while we had data and basically wanted to finish the analysis was not a pleasant process. So I am very glad to say that we are solving this problem for LSST before data arrives. David already talked about the core cosmology library that is on the archive now. For LSST right now arrives, we can focus on more physical aspects. And I encourage you to download yourself whatever project. You don't need to be limited by numerical accuracy at this point. So on from numerical accuracy to some more physics. That is systematics, modeling, and mitigation of the residual uncertainties. So after long discussions, we decided on a baseline model for our systematic uncertainties that consists of 20 parameters. We have linear galaxy bias for each tomography bin. We have photometric redshift uncertainties in form of a simple shift parameter for each lens and source tomography bin. We allow for multiplicative shear calibration uncertainties, so for some uncertainty in shape measurements in each bin. And we consider two different models for intrinsic alignments. This may sound very simple as a systematics model, but I would highlight the 20 parameters compared to 6 cosmology parameters. So I think that the most type of analysis in the literature so far. The fact that galaxy biasing definitely is not linear, and we know about this, but we need to make sure that it doesn't bias our analysis. And then for the rest of the parameters, this is again our arbitrary, or rather linear parameterization, which certainly is not the underlying truth of the universe. So we need to make sure that this choice is sufficiently flexible for our analysis. And I should say that we committed to this model and put it out on the archive before we really looked at the cosmology constraints. So let's start with the incomplete model. So as I said, we know that there's physics out in the universe that's not included in our analysis. So we better make sure that this does not bias our cosmology results. And I'm giving an example here in terms of galaxy bias, where we chose to just use a linear model in the analysis because it's so simple and fast and relatively user-friendly. And in order to get away with that, we had to decide which data points from our analysis to discard. So we used the theory pipeline to calculate fake DES data that now includes higher order biasing, in this case quadratic and tidal quadratic bias, and analyze it using our linear model only. And if we do this going down to a 4 megaparsec scale, then we find that in this fake analysis, our MCMC recovers cosmology parameters that differ from the input in our theory calculations. And then as we discard more and more data points and restrict ourselves to more and more linear scales, we come back to recovering the input without a bias. So that's how we get away with linear bias. And we do similar tests to make sure that baryonic physics does not bias our cosmic shear analysis, which assumes a dark matter-only power spectrum. Sorry?
The baseline without.
Yes. Yeah.
And then since the error is not start partially go from the baseline to the next. You add into the DS squared, not change too much in the error.
Well, so we only add BS2 in the input, not in the analysis. So this is still only marginalized over B1. And this top line here is just to make sure that if the model is the same as used in the input, that we actually recover the input cosmology. It's a sanity check, or also a check that our priors are not too asymmetric. And if you think that the error bars don't decrease as much as you would like going to small scales, that's in part because we don't have a good fit anymore, so the likelihood gets distorted. And then we continue this game of putting a more complicated input into our theory code and analyzing it with a simpler model. So specifically, we generate theory input where galaxy bias evolves within each redshift bin, analyze it using just a constant bias in each redshift bin, and we play similar games with intrinsic alignments, shown over here. And then we also check what happens if our priors on these calibrated systematics, namely shear calibration and photoz's, are off. We systematics that's robust enough for the SU1 analysis.
When you say that you see what happens if your priors are off, that is caused by like half a sigma of your prior?
1 sigma in each redshift bin coherently.
Okay.
So that's pretty pessimistic, I would say. So we've all agreed on we is in DES and have not looked at cosmology yet. That's because we decided that we did not want cosmology results to be influenced by our own prejudices. Others may have gone in and say, oh, we want to find that DES and Planck perfectly agree. Others, who are on the job market, for example, might be interested to have a more interesting result and cause a splash. But we don't want the louder of those two parties to win. So that's why we decided to hide the answer until we were ready to write it up. However, as it turns out, blinding cosmology analysis, especially at a correlation function level, isn't that easy. In some particle physics searches, for example, you can just shift the energy scale, fit the bump without knowing where exactly it is. But that's not as easy for power spectra or correlation functions, because here many of our systematics are directly also live at the source or lens and modify the 3D power spectrum and then get processed into our observables. So at the end, we decided to do a two-step process where we rescale the shear catalogs. So each galaxy shape gets multiplied by a random number known only to one person in the collaboration. And that means that, for example, we can't read sigma 8 from correlation functions anymore. And our analysis codes were also hacked so that the output cosmology parameters were shifted. If you ran an analysis and just plotted a chain before unblinding, likely your results for omega meta sigma 8 were close to -1, -1, which was definitely difficult to explain in some job talks on blinded data. But the idea was that if you tweak one of the systematics models, we want to see whether the contours shift or not, but we don't want to have any indication where we are with respect to other experiments. And this scheme still allowed us to do quite a number of null tests. But for example, it already prevented us to look at the consistency between galaxy clustering and cosmic shear, because the amplitude of reclensing was modified, but not the amplitude of galaxy clustering. For that, we have to inject fake galaxies or remove galaxies such that the correlation function gets modified the same way as cosmic shear, and we don't know how to do that at a catalog level. And I should state that we also had agreed not to overplot theory and data until we unblind, and that we would state all post-unblinding changes in the paper. So there was then, I would say, a week of yelling at the collaboration meeting. Are we ready? Are we not? And after somewhat sanity checks that were within our blinding scheme, as we realized at the end, we were ready to open the box. So one lesson that I would like to tell you from this process is that please, if you do this, agree from the start whether you do blind parameter measurements or blind model testing. Those are two very different things. And that's probably what held us up by a week in Chicago, deciding whether we can unblind or not, and what sanity checks we're allowed to do.
I thought you would say, please don't yell at the comments.
That too. And of course, it's also clear that complicated blinding schemes can introduce bugs. So my personal guideline for this by now is that somebody really knowing what they're doing should not be able to unblind unknowingly, while those who don't really know what they're doing should not be able to unblind knowingly. And then we open the box and get these beautiful constraints, which for me are the main DS, that is the main plot for me from the DS 3x2 cosmology paper. The green contour here is our cosmology constraints on matter density and S8, this amplitude of structure growth from cosmic shear alone. Red is galaxy clustering and galaxy-galaxy lensing. And keep in mind that both of these are marginalized over a large number of parameters. We always have 6 cosmology parameters that are marginalized, or 4 that are marginalized, 2 that are shown, and then the nuisance parameters, 10 for cosmic shear, another 10 for the lenses. So there's a lot going on in the background of this plot. And then finding this beautiful agreement between the two measurements, I thought, wow, it works. We were able to control our systematics. And because they agree so well, as statistical tests also tell us, we can then combine them to get a blue contour, which is the combined DSU1 3x2 result. Of course, now that we've unblinded, we also have to look at other experiments. So here's now the comparison between DES and Planck, TT and low P only, without explicit CMB lensing for the best comparison between DES and the early universe as we could do. And how to interpret these contours may vary across different groups. You clearly see more than one sigma shift in this plot, but Bayesian evidence ratios also tell us that these two contours are still consistent in the full parameter space. So there is no reason yet to get excited about tension between DS and Planck in lambda CDM, but I should also point out that other lensing analyses, namely CVHLS and KITS 450, basically lie on the same side here, towards low omega m, low S8 compared to Planck. So the next years will be quite exciting. In the near-term future for DES, there will be cluster cosmology results. And then over the next year or so, we're moving on from DSU1 to year 3 dataset. That means a threefold increase in area, and likely a shrinking of the of those contours by maybe a factor 2 or so. We will also push to smaller scales to include more nonlinear physics, further improving our constraining power, and do a joint analysis of the 3x2 analysis and cluster counts. So hopefully these contours will shrink by more than a factor of 3 within a year. And with that, I hope we'll have a good test run for combined analysis of clustering, reclensing, and galaxy clusters. And we'll be ready to tackle the future. For the rest now, I will focus on LSST. That's why we're here. So let's just say we go from about 26 million source galaxies to over 20 billion. That will be quite an increase. And yes, this is really happening. this is the summit view this August. So it is being built. And if you look at the timeline, we are here now. Most things are quite on track. I don't need to go through all of this. Rest assured that people are carefully tracking the progress of this project. The survey-like operations will start in late FY 2021, and we're pretty much on track for that. So we better get ready. And there's an even collaboration in the Dark Energy Survey working on this already. Let me introduce you to the Dark Energy Science Collaboration. This picture is a bit outdated. By now, I think we have over 700 members, several hundred of which are actually active. And together we prepare for cosmology analysis with the LSST survey. This is organized in 6 cosmology science working groups. So we want to do cosmology through galaxy clustering, galaxy clusters, strong lensing, supernova weak lensing, and a joint probes analysis. And this goes hand in hand with a number of other working groups that simulate cosmology, the survey, study sensors and everything, so that we can together characterize the performance of the whole experiment. But obviously we have lots of work to finish until first data, and lots to learn from DES and other ongoing surveys. So please come and join us, because LSST cosmology will be a big step up from DES. Here I'm showing the projections of the joint cosmology constraints for LST year 10 from galaxy clusters, strong lensing, and the 3x2 point analysis. So the equivalent of the analysis that I just showed you for the Dark Energy Survey. And then the combined analysis with stage 3 priors shown in black. This was a recent paper, the science requirements document by the desk collaboration. And these, I should say, these are the first joint forecasts since there's a science book. So this reflects how much our understanding of LSST and systematics has evolved since 2009. And for this forecast, so we split systematics into 2 classes. Those that we call self-calibrated. That is where we use the constraining power of the data to learn about galaxy bias, intrinsic alignments, and the cluster mass observer relation. And then external calibrated ones, such as photoses, shear calibration, and photometric calibration. Of course, again, these lists are not complete. Our work is not done here. We want to prepare for all the important known systematics for LSST. And one could start this by asking, what's the dominant known systematic for LSST cosmology? But then the first answers are, we need more details. The answer won't be that simple. We need to be more specific. Namely, we need to specify which probes we're talking about and on which scales. But a spoiler ahead, likely the answer will probably involve galaxy evolution. So we set out and specify a data vector in which probes and scales. And then we can do the same exercise as we did in DES and write down all the possible systematics we could worry about. And then we have to come up with a joint parameterization that describes the impact on all the different observables that go into our analysis, which already is a highly non-trivial problem. And then we have to prioritize. So we want to constrain the parameterization and decide which priors or nuisance parameters will help us most in the future. And I'll talk you through that process in a cartoon. So right now, we don't have data, but we have theory and simulations. And we're building an analysis code. So we can do the same basically scale cut study or parameter bias study that I showed you for DES. We generate fake data, analyze it, and check how important the systematic is. And if it's important, we go and refine. So let's look at this in a cartoon. Again, in a theory streamland, we would know the input cosmology, do our analysis, and recover that input cosmology basically without bias and tiny error bars. That would be great, but now in comes the systematic effect. If we don't know about it and just do our analysis as before, we end up with parameter bias. Here now we have the truth to help us to know, oh, we ignored something. Let's try putting in the systematic. Then we marginalize over that parametric model. And we recover our input cosmology again, but now at a price of increased uncertainty due to systematic uncertainty. Since this is quite a loss in constraining power, we might go out use additional data sets to better understand this astrophysical effect and put tight priors on our systematics model. With that, we could then end up in a situation like this, where we regain some of this constraining power. So let's go to some examples. As I said, likely our analysis, our key systematics will include galaxy evolution. So let's start with one example, the intrinsic galaxy shapes, where the intrinsic alignment of the background galaxies is a key contaminant to weak lensing. So just as a reminder, the weak lensing effect, we have a background galaxy, and then the large scale matter distribution between us and the galaxy that does the lensing. So that causes some tidal alignment of that background galaxy here. And then we have also galaxies that live at the same redshift as this dark matter blob. And depending on what galaxies they are, they might also be influenced by the same tidal field that does the lensing. If these galaxies are elliptical galaxies, their halos will align in a tidal field and cause a spurious alignment that mimics cosmic shear. And it will cause an anti-correlation between the galaxy that aligns radially here in the tidal field and the lensed galaxy that's lensed tangentially. And this could be catastrophic for weak lensing if ignored. Has been known for a long time that this is an important systematic. Here is one example of how important this could be for LSST, using realistic assumptions about the LSST galaxy distribution. So if we ignored intrinsic elements in our cosmology analysis, we could end up with estimating W naught of minus 1.8 with error bars of maybe plus minus 0.1. WA also significantly not different from 0. Wow, cosmology got very exciting. But we know what's causing it, so we better study intrinsic alignments well. If in this example we then marginalize over a 17 parameter intrinsic alignment model, we recover the input cosmology for a broad range of input IA scenarios. That even this gives us flexibility not only for the redshift evolution of intrinsic alignments, but also for the shape of the IA power spectrum. So that's nice, but keep in mind 17 IA parameters compared to less than 10 cosmology parameters. We don't want to be this excessive for each systematic. Another example is galaxy bias. In our baseline forecast, as in the science requirements document, we only include linear bias. So we think that we can reliably predict galaxy clustering on large scales. And here's a forecast how well we will do using the 3x2 point analysis with LSST, so weak lensing in galaxies on scales down to 50 megaparsec for galaxy clustering, and shear down to where baryons become important. And so far, focus on the blue contour only, that's large scales only. And then if we do a lot of theory development and invest in great simulations, such that we can also reliably model and marginalize over the clustering of galaxies on small scales, such that we can analyze our data down to 0.1 megaparsec in galaxy clustering. This would lead to this more than factor 4 improvement in constraining power. So that's equivalent to doing the LSST linear scale analysis only on more than 2 full skies, which obviously has some practical problems. So it's very much worth pushing down to understanding small-scale galaxy clustering. However, this obviously only works if our model is accurate enough. And likely we will end up at the end in a situation where our models are pretty good, but not perfect. So like this magenta contour here. And obviously in the real analysis, we will not have that black star there telling us how well we're doing. So what we need to do now is not only work on precision, but work on consistency. So for that, now we need the different individual probe analysis. We need LSS, weak lensing, galaxy clusters, supernova and strong lensing to their own most precise analysis as they've built up to. And then we look for consistency. So then we might end up with a situation like this. We don't know where the truth is more, but we have results from each working group. And well, now we can do physics. What physics is still unclear. I wouldn't claim new physics quite yet. We should first start by looking at the scale dependence, obviously, and whether the contours move together. We exclude nonlinear scales. We should also ask whether the contours shift if we change our galaxy or cluster selection function. That might give some hint of what's going on. And we can also, of course, go out and calibrate with more accurate measurements. So for photoses, we can get more spectroscopic measurements. For galaxy clusters, we can get more X-ray measurements of a low scatter cluster mass proxy. For galaxy shape uncertainties, we can compare to space-based lensing, where I have an example here of what galaxies look like in Subaru data, which is probably the closest we have to LSST right now, and what they look like in space-based imaging. And obviously, there are cases where what you identify as one and its shape quite a bit with improved imaging quality. Matters and how much it contaminates our shape measurements. All of these techniques are inherently expensive because we need more expensive measurements to calibrate our photometric optical data set. Another option here then also is to cross-correlate our cross. Here I show how well we expect to be able to calibrate the bias in our shape measurements by cross-correlating LSST lensing with CMB. This paper led by Emmanuel Shan, looking at various data combinations, lensing only, and then including galaxy clustering as well. But the upshot that I want to tell you here is that with this cross-correlation, we should be able to calibrate uncertainties in galaxy shapes to the sub-percent level. And that's are the most complicated ones, the most headaches for the cosmic tree analysis. The remaining thing I would like to keep in our assessment of what could be going wrong change if we knew that the Planck best fit was over here. Check what's going on been different in this case. But with that question in the back of our minds, and the idea that we probably want to discuss blending strategies for LSST at some point, this to precise and accurate cosmology constraints. Basically, we have to iterate until we find consistency among all the probes, because only that means that we finally have a sufficient model for all observables, and we can actually combine them. And with that, then we get cosmology for which we have the best hopes of it being accurate. And because no cosmology talk is complete without a pie chart, let's talk about let's talk about parameters in LSST analysis. It's about 5% of parameters that we understand quite well, and these are our cosmology parameters. Then there is another 25% for which we can hopefully make progress with laboratory experiments. And these are related to observational systematics and sample cuts. So we can study our CCDs, we can vary the selection function. And then there are systematics parameters which come in two flavors. The systematics, which are survey-specific, and astrophysics systematics that are probe and survey-specific. But of course, sample cuts and systematics are highly interconnected. So I guess we can say it's 95% systematics. And we really need to use this dependence on survey and probe to cut through this enormous parameter space and understand what's going on. And that brings me to my conclusion. Namely, we are entering a decade of massive cosmology surveys, among them LSST. So their cosmology constraints will be systematics limited. A lot of our progress and constraining power will be in systematics control. And for that, we can use the different surveys and different probes measured within each survey to control systematic, to check systematics and control them. First of all, we can identify them by looking at the consistency of probes, and we can maximize constraining power by self-calibration of systematics parameters and by combining the different measurements. However, efficiently, we basically need collaboration across surveys and wavelengths starting right now. so that later on we are actually ready to collaborate on data projects with each other and haven't taken some steps along the road that make it impossible to do cross-correlations or efficient multi-wavelength analysis. So that's work. If you're interested in doing some of this for LSST, here's the website of the Dark Energy Service. And you can, of course, also always talk to Chiwei, David, Katrin, who have leadership roles on the desk, and everyone else of us who's actively working in it. Thank you.
So we have plenty of time for questions.
So you mentioned the search for systematics through the consistency between multiple probes. I was thinking if there could be a case where actually there is no consistency between different probes. Let's say, for instance, like we see now H0 and CMB, right?
Mm-hmm.
So do you have an idea how to deal with that, or what are your thoughts on that?
That could, I think, of course, we shouldn't just blindly inject random systematic templates. This should always be based on physics intuition, and each systematic that we put in, if we see a discrepancy, needs to be physically motivated. We can only combine if we have a sufficient model that includes both systematics and cosmology. So if we find that this discrepancy exists, then we have to put in at least some discrepancy parameter on the cosmology side before we can attempt a joint analysis and see whether it becomes more severe or goes away. So basically, in many ways, the distinguishing between systematics and cosmology parameters doesn't really make sense. On the level of the analysis by itself, they are all treated equally. As cosmology modeling.
Thanks for the very nice talk. If you would have to make 2 more pie charts, would it be easy for you to do? One on what are the systematics and how much do they right now influence what we have? Like photosy, baryonic effects, intrinsic alignments, like which one is the most important and going down? And another one where you would say you hope of that we will tackle that by the time LSST is coming, and like where you think it will be super, super difficult and we actually will not be able to do it.
I think the second one would be a great hack at the desk meeting. This will really take input from experts on all the different systematics. For the rest, we can, of course, only, for the first one, we can, of course, only put into a pie chart what we've already parameterized. But for those that are already in the code, that would be easy to do.
More questions? I have a practical question. If, for those of us that want to enter the desk, what should we do? Go to this webpage? No.
Since we're here, we should in Chiwei, David, Katrin for witnessing LSS, more of the computing side, Tessa, so on here.
So the one thing I would like to say is that it's super, super easy for anybody who has LSST data rights, so that's important, to become a member. You basically go to that web page, you sign up, and you can get access to all the information that is out there just to get you started. So we wanted to make the hurdle basically as low as possible to really get people started. And then you can see a little bit more what's all going on. And then, as Elisabeth said, like just reach out to people. Everybody is super happy to get more help with everything. But it's really easy if you have data rights, and a lot of people do have. So. So people can, instead of signing up for becoming an LSST desk member, they can sign up to become an observer. But it gets difficult because, I mean, okay, right now there is no data, so people are relatively relaxed. But as soon as data comes in, so you can become an external collaborator, But then you have to have like special skills that nobody else in the so it's not so easy, but it's definitely possible, and more people. So if I would be Steve Kahn, I would say please give us money and buy into LSST. So that's the other option. So institutions can buy into it who are not in the US. So
that's rather unfortunate terminology, that you can be an observer until data arrives.
Going back to this, so there was this recent paper, the kids paper, where they showed that, or one of the points that we're trying to make there is if they calibrate their photosees using Cosmos, which is what HSC and DES have done, then their contours shift upwards towards where DES is, basically. So I guess the question is whether or not for year 3, we can expect that the redshift calibration will be done differently or not for DES, and where there would be like better spectroscopic samples to use for that or not. If you can say, I don't know if you can say.
So first of all, I think that shift in that direction, but it was less than half a sigma?
Yeah, so
yeah.
It's discussing half a sigma shift, so who knows? But
yeah,
just wondering. I guess forget about that part of the question. The other part is, will there be like other like better spectroscopic samples to calibrate with, or is it still going to be Cosmos?
The spectroscopic samples will be very similar.
Okay.
But we are working on major improvements in the PhotoZ methodology.
Okay. Okay.
Moving beyond BPZ.
Yeah. Mm-hmm.
More questions? No? So let's thank Elisabeth again.
And if I can just make in my remaining minute one more comment about joining desk. If you go to our website and find this science roadmap, don't be intimidated. It was written by humans, so it is also human readable, and there are people here who can interpret it for you. So don't get scared if you see a lot of technical terms.
I won't be able to pronounce.
You write Portuguese. Okay, so the...
yeah, but you should use this.
I prefer to use mine, so...
No, but this is HDMI.
Okay.
That's the problem.
Oh. So
do you have an HDMI port?
No. So I need this one. Okay, let's see.
It wasn't working yesterday, so I hope there are no problems.
Oh, it doesn't work?
No, but let's try. Yeah. Okay, seems to be working.
I could just take my...
Okay. Better work this one. Okay, so now we have Reinaldo Rosa, who will tell us.
Microphone.
You should put this somewhere not very close to
Here? Here?
somewhere down, so that not very close to your neck. Yes.
Hello.
Okay. Okay. So now we have Reinaldo Rosa, who will tell us about challenges for galaxy morphological classification from large surveys.
Okay, so thanks, Roger, and organizers, for this wonderful meeting and for the opportunity to show you actually just a glimpse on the problems we are facing and solving for galaxy morphological classification, especially taking into account the large surveys. Okay. The work I'm going to show you has been the participation of all those guys here. Okay, I'd like to mention my students, Paulo Barchi and Ruben Salter and Vu Shun. Salter and Shun are here. And there is also a poster that has most of the details I'm not going to show you because I don't have time here, but you can go to the poster and discuss many features of this work. Okay, the outline of my talk will be, I will start trying to answer these very common questions for us. These questions, why galaxy morph classification is so important. I guess everybody here knows. Then I will point out the main motivation, that's the LSST data that are coming soon. And I will take this opportunity to show you a new platform that we have for morphological analysis that we call SciMorph. So I'm confronting that with the traditional one that we call CAS for concentration, asymmetry, and smoothness. And especially one tool that we call gradient pattern analysis. That's the novelty on this talk. If I have time, I will also show you the non-Gaussian Coulomb-Frey space characterization that we have done for 1 million samples. And I will, for my final remarks, take into account the main computational challenges. Okay, so why galaxy morph is so important? There are many reasons for that, okay? But we are in the era of larger surveys, so we need to know more about all those things, galaxy formation mechanisms. If there is a hierarchical merging, dark halo, gas in fall, isothermal spheres, and that's very important, no Gaussianity everywhere. So also galaxy evolution paths, galaxy morphology at different environments, galaxy dynamics, take all the functions for the fundamental parameters, galaxy and universe evolution, and so on. What's important to stress here for larger surveys are the galaxy morphology at different environments. That's one hotspot point in our project. And this is related also with the elliptical galaxies. That's nowadays the classification of elliptical galaxies in this zoo of galaxies. Even we have the traditional Hubble and Fork-2 schemes. It's taking more and more complex. Especially when we are taking into account the Hubble time, dynamical time, cooling time, star formation time, as a height, merging time, dynamical friction time, and so on. For a practical point of view, in order to compare our results and validating models, we would like to go to this kind of dependence in physical size as a function of a redshift, the same for angular size, age, and morphology. By the way, this is the title of our project in the FAPESP, what drives the stellar mass growth of early type galaxies. Born or made, the saga continues, okay? It's almost like Star Wars. It's a galaxy wars. So that's FAPESP. So most of the things I'm showing you here comes from this project. So, of course, we are talking about galaxies that are in catalogs. We need very good catalogs, okay, from big data. That's very crucial to develop what we call now the era of data science, both in scales that we call astrophysical scales and also, of course, in cosmology. The main motivation is the LSST telescope. It's going to generate what we call data cubes. And it's in the mainframe of what we call data science. Okay, as has been defined by Holt and collaborators in 2010, it's relevant scientific discoveries and its theoretical paradigm evolution depend on intensive analysis and high resolution interpretation from data cubes. That's they call 4V. Many people are doing that using larger surveys as SPIDER and even from simulations, Illustris. We are working on that. As I am in astrophysics meeting and cosmology, I would like just to stress the concept of data mining from big data. When you say data mining and when you say big data, you are talking about a huge volume of data that we call 5Vs. Okay, we are talking about from petabytes to exabytes. Okay, we are in this range in this next 10 years. We are talking about high velocity in terms of workload. It means around 1 terabyte per hour, okay? So LSST is going to give us 12 terabytes per night. It means in practice almost 5 terabytes per hour. And we will have a variety also. In our case, we are going to try to do mining of 2 different classes at least, okay? The early type galaxies and the late type ones, or in a more morphological meaning, we are talking about elliptical and spiral galaxies. So we have 2 in many subclasses, as we know from the, for example, the fork 2 scheme. We have also the value. It means that we have a mining quality from 2. Of course, we will have many low quality data, okay, when you are doing this classification. So it's very important to apply many techniques to minimize the classification using low quality images. And the 51, that's a new one here. That's, from my point of view, is the most important one in this meaning of big data, is the virtuosi, the virtuosism of the 3 main components in our approach. It means software, hardware, and peopleware. We need to have as much as we can the high quality in those 3 segments, okay? That's very, very important. And I'm going to show you some calculations on that. Okay, what you have done in the statistical computational mainframe, we call that discriminant analysis from big data, okay? The idea is to have like 2 classes. We do any operations on those metrics, and we got parameters that can distinguish both patterns. Usually we see each one in a histogram like that, okay? And we see how we can separate it, both classes. Some parameters could be very good doing that. Other ones are not so good, like this. And that's the main challenge in this approach. And after that, what we need to do is to construct this parameter space to see if the separation is enough to start to training, for example, machine learning. And also after convergence, we can use also deep learning approach. Okay, so that's the idea. We need to go to the deep learning one, okay? And the deep learning we are working in a very comfortable way in a convolution scheme that I'm going to show you. So we are talking about in solutions of hardware and software in the same domain. Okay, what are the main challenges now, taking into account the large survey era for morphological classification? Of course, the main challenge is to be as fast as we can. So to do that, take into account the amount of data that are coming, the workload, workflow, in order to optimize our workflow, we needed to have it like this. We need to do competitive science. You need to face the classification of 1 billion galaxies in 4 months. Okay, I will show you why we get this number. Okay, but it's an average that goes to this 1 billion galaxies in 4 months. Otherwise, you are not being able to do interesting things. And we are going to use, of course, the machine and deep learning resources that most of you, I think you know. The fast morphological classification is important, starting from this binomial classes, early type and late type, okay? And why that's the 2 important challenges in our approach are modeling. After you classify those galaxies, you go to the late type and do a modeling using, for example, Gauffat. Okay, here we have many challenges, computational ones. For example, right now we are working to run the Gauffat, at least the model of Markov chain Monte Carlo using GPU, okay? That's very important too, in order to get the brightness for different Sarsic index for those galaxies, taking into account the different redshifts and also different environments. Also, it's important to have this Cullen-Frey non-Gaussian characterization. Nowadays, we are working with more than 1 billion canonical samples to classify in a very fast way which kind of PDF with which kind of non-Gaussianity is in a very precise way describing the distributions of any variable, okay? Okay, in this talk, I will just show you very quickly what is GPA, okay? That's very important. If I have time, in a few minutes, I will show you those results that I consider also very interesting for this audience. And if I have time, I will show you also something about machine and deep learning. Gradient pattern analysis is a new technique to try to classify patterns, take into account the gradient field of the image. We are not working straightforward on the amplitudes, on the pixel values. We are working on the gradient calculated from the matrix, okay? So what is able to quantify with that is the breaking the bilateral symmetry, okay? It's very interesting to characterize that. Bilateral symmetry take into account okay, all the 4 axes we have in the square matrix, or the rectangular one, are the horizontal, vertical, and the 2 diagonals. If you apply that, this is just an example for 2 patterns, one for a spiral and an elliptical. So we got the gradient field like this, and what's important to know here is the first operation we do is removing all the symmetric pairs. What's symmetry here? They have semi-moduli and opposite phases, okay? For a tolerance, of course. And in this position, you'll be many symmetric pairs here also, and we start to remove that. So, of course, if you take a Gaussian like this in 2D, x and y just amplitude, you start removing all vectors. So the gradient bilateral symmetry will be 0. There will be no pairs of asymmetric vectors from this kind of matrix. The detailed description of this has been published this year. So we call gradient pattern as applied to galaxy morphology. So I recommend you take a look if you are working on those kind of problems. It's also very useful to classify not only galaxy morphology, but you can apply also for large structure formation from simulations and also from real data. Okay, how it works. The first gradient moment we can see it's not a statistical measurement, it's like a geometrical one. Okay, so when you start breaking symmetries, this is elementary matrix 3 by 3, just to show as it works. Okay, here will be 0, 0 by definition, and from here, when you have the amount of asymmetric pairs different than 0, greater than 0, you use this formula. Okay, you just do the triangulation among all vectors, alive vectors. When you have irregular patterns like this, it to take a very special value that tends to 1. Okay, and when you break symmetry, you are increasing this due to this, increasing the sides of triangles, the connecting lines. So that's the connecting lines, that's the number of asymmetric vectors normalized by that, and we have shown that goes to 2 in asymptotic way as you increase the size of matrix. Okay, so that's 2 examples again, just it works, how it works. It's very interesting because when you start to break in symmetry, okay, like a fragmentation like this, so that's also very important for spatial temporal patterns, you start to get these measurements that can tell you how the central source is working to decrease or increase the bilateral symmetry. Of course, if you have a central source like this, when it's increased, all the vectors will be more aligned concerning this central amplitude. So it decreases a little bit, okay? From this approach, we can actually calculate 4 gradient moments. We call gradient moments because all of them are generated from the gradient field of the matrix. Okay, we call this G1. So we can write this as the norm, a matrix of the norms, matrix of the respective phases, and also we can write for each vector, a complex number. Okay, R, for example, the first vector will be R11 plus I, the complex part will be the phi11. So we have this representation. We have derived many quantities. This is for this pattern, okay? We can calculate the G2, that's a kind of measure that takes 3 values, 0 when there is total symmetry, 1 when all the vectors are laminar, like a laminar fluid, and goes to 2 when it's totally, all pixels are totally different, okay? They are in a random distribution, but there is no repetition of any value. Doesn't matter the size of the matrix. In a random matrix, for example, you need just to check if there is a repetition of values in a real domain. We can do the same thing to the phases, and we can calculate this for G4. That is a kind of entropy. So we have 4 parameters, and that's what we have done to the galaxies. Okay. Of course, that's the processing that we are doing on the galaxy, but we have also the pre-processing time. Pre-processing time from the original field, we take a stamp. The stamp is selected, then we cleaned up this, and then we segmented that using a special mask. So that's the stamp already done in order to be analyzed by GPA. The analytical process and the results that we got using this amount of objects, okay, 56,000 stamps from the Galaxies USDSS sample catalog. Is in this way. You use the traditional one, okay, using concentration, asymmetry, and smoothness. I'm not going to talk about the technical details on that. I suppose most of you know that. But if you want more technical details, you go to the poster, okay? And that's the results we have get. So here is the traditional system. We have computing. We have calculating this distance between the two histograms, taking into account this formula. This is also introduced in this paper. This is very useful formula for everybody in many applications, general applications. We just calculate and use the box counting approach, taking into account both areas, the blue and the red, and also the heights of each one. Okay, so this is the part of the heights, and here the parts for areas. When there is superposition, it's to be the distance will be 0. When they are totally separated, the distance goes to 1. And here we have the time for that. Take into account to use it a very new architecture that was, let's say, competing with GPU. So we use here the K and L from Intel multi-core with 68 cores. It was we are trying to show that it was much more powerful than GPU, but we didn't get this result, unfortunately. So, but anyway, here are the results. What we can see from here, the performance is the inverse of time. And we see that with GPA, we got the best separation and classification, taking into account those stamps. Okay, if we go to 10 to 6 to 10 to 9 objects, okay, the computational resources we are waiting for. Now we have this fat node with this configuration, okay. We are working on much more, it's almost 1 million objects. The result is in the poster for this one, okay. We still don't have big data here, okay. We are taking this in less than 10 days. The next, in 2019, we go to DES and BLIS. We will get 3 million objects. That's big data. We are working with more than 100 terabytes of data, and we are using also deep learning to face this problem. Next, 2022, when it starts to have some first stamps from LSST, we will go to these 1 billion objects. So we are talking about more than 100 petabytes, and we still don't know which will be our virtuosi computational systems. We are working on that. But what do you know? We know that the single computational complexity should be improved 100 times if you want to face those kind of data in a competitive way. The download data should be less than 0.5 seconds. Find object retrieve data and more should be also in this range. Morphological analysis and the classification using machine learning is like this. So you need to improve all of this by 100 times. And there is an empirical formula for 1 billion objects, taking into account fat nodes when you have more than 128 cores, okay? And this empirical formula is very interesting. It's called Cosmology multi-core empirical formula. So what's the time to process 1 billion objects, okay? With a typical size coming from the LSST data, for example. We have this empirical formula. This parameter is for loading time, okay? We can go from 1 to 10 here. When it means 120 megabits per second. The pattern analysis for beta, it's in terms of the number of cores. So we have, when it's 1, it's 128 cores, so we can going to increase that. And classification is just those 3 index. So, is it possible to analyze, to classify 1 billion galaxies coming from LSST in a very short time in terms of useful time in order to understand and do everything scientists, the science does? Yes, if you apply this, you can get this one for 2022. You are going to get the maximum values here. So if you use it today, if you apply today our resources to do that, you will spend 3.5 years. Pushing that to the limit here, you will spend just 124 days. So it means around, if you ask me, how long you take to classify 1 billion galaxies, you say, let's say 3 months, around 3 months, okay? The strategy to improve the performance is go to deep learning. So if you use deep learning, we can reduce this by half. So that's also one next step we are going to do, okay? So I need also to say that another important challenge is we have a supervised and unsupervised approaches. I didn't say that. And we have also balanced and unbalanced samples. This is also a problem. We still need to improve the supervised machine learning for galaxy morphology. Galaxies is right now in this number, the catalog. We need more citizen science trying to improve those numbers. Let's see. I have some remarks on computational resources. Okay, actually, I'm not going to read everything here, but the best solution, we need our dedicated non-concurrent deep learning resources, okay? Because if you have a supercomputer in USA, they say, we can use that to do classification. It's not enough. You need to have your own machine, okay, using deep learning with your expertise in the 3 segments, hardware, software, and people. Otherwise, you will not be able to do that in the time we have calculated from the empirical formula. Okay, there are many things to talk about this, but our SciMorph is already done. Everybody here can use that, okay? We call SciMorph. So we are able to use that also in the deep learning approach. Just go to the poster and see the last results we got. This is just to show how the convolutional neural network works. What's important here is to say that all things here can be solved as a number with the new technology that we call TensorFlow. Many of you know that using TensorFlow, they go forward for a matrix like this, and so that's very, very fast. That's our new results using deep learn, and we can classify not only spiral and confronting to elliptical, but we are doing that for many different classes. If you do 2 classes, the classification using deep learning is almost 100%. Okay, if you use a superclass, so we lose some performance here, but is not so bad. As I told you, I would like to just to show the Coulomb-Frey non-Gaussian characterization. This is another approach. Okay. Also, it's important to classify elliptical galaxies because you know that for elliptical galaxies, the distributions of the velocity distributions are non-Gaussian. Okay. This is one result that we got in the paper published in 2017. This is a recent result. So we have a work on this Coulomb-Frey classification. So the best, we have also applied this to the Virgo simulations. This is not illustrated, so, But anyway, there will be not new surprises if you also apply to Illustri. So we got the classification here for this. It's totally non-Gaussian, okay, in this Cullen-Frey space. Kurtosis against the square of skewness. And that's it, okay? I would like to take the opportunity just to advise you about this conference that is coming for next year, Conference of Computational Interdisciplinary Science. There will be a special session that I'm the chair, me and Cesar Careta from Guanajuato. So I invited everybody here, if you are interested, to apply, to submit a paper to this conference. It will be in Georgia Tech University from March 19 to 22. Okay, thank you.
So, questions, let's take for one or two quick questions.
How do you make sure that these algorithms are Serbi invariant? That you can use, training with Galaxy Zoo, and then can you expect them to work in Sloan and, I don't know, in DES and in different Serbis? Does it depend on the training set?
Yeah. Your question, we cannot guarantee if you are using a machine learning approach, because machine learning is based on the ranges that my parameters will be. Okay, but I can guarantee that using deep learning doesn't matter. Okay, it's totally unsupervised. So we have now machines that are totally able to learn. Doesn't matter which. If you see how the convolutional network works, they are in a 100% of classification for the whole patterns that are in the university libraries. They use it for pattern recognition. Okay, there is no mistake. If you take a cat and a dog, for example, you can mix the images. You can put a piece of something in the face of the cat. Even that, deep learning is saying it's a cat, it's a dog. It's impressive. Okay.
More questions?
So the way to solve is deep learning. Okay.
Hi. So I just want to be sure I got it right. So when you compare your gradient pattern analysis against the CAS system, so as I understood, you are learning a dictionary, and may I say that the dictionary from the gradient pattern analysis carries more information or more discriminative power against CAS?
CAS, the problem of CAS actually is not a number like a parameter. Why? Because concentration is the bright concentration rate, actually. The smoothness is you just smooth the image and you do the correlation pixel by pixel and take an average. And the other one is the concentration, asymmetry. Asymmetry, you do the same thing. You just rotate by pi the image and confront with the original one. So it's not a parameter, no? So it's now you are in a new paradigm. GPA brings a new paradigm. It's not statistics. It's just like a digital print of that pattern. That's the new paradigm using GPA.
And did you try, just as an exercise, like for instance, if you apply a variation autoencoder, how much compressibility can you have in the?
Yeah, we still didn't that, but that's a good point. Yeah, let's discuss about that.
Okay, so let's thank Reinaldo again.
Thank you.
Go for lunch, and we meet back at 2.
Olá.
Olá,
Muy
tudo
bueno,
bem?
interesante
Ah,
el
gracias.
trabajo.
Gracias.
¿Sabe? Te quería preguntar, ¿cuál es el benchmark que usaron ustedes? Tú dices que es un 100% de recuperação respecto de qual?
O benchmark são que eles chamam de universitário, padrões universitários. Tem um repositório, todas as universidades. Não. This is around the world, internacional.
Não tem nada a ver com o project.
No. This is actually now it's supported by NVIDIA. NVIDIA is NVIDIA that that's the responsible to. Opa. Obrigado.
We are talking to the audience.
NVIDIA is the responsible to the a fabricação das GPUs.
Ok.
Então, eles oferecem cursos de treino e eles constroem esse benchmark database.
Entonces, en este momento están en condiciones de lo que se espera del LSST, van a poder hacer clasificación y la efectividad la han estudiado en función de Redshift. Ya se sabe hasta qué Redshift van a poder hacerlo. Pero también
She knows very well. Let's ask her. He's asking me the redshift range for LSST. The maximum one, 4, 3 point something.
I mean, there will be some rare higher level galaxies, I'm not sure.
Yeah, but then it's a new stuff.
So this is, I'm going to talk more about the galaxy content of
Yeah, let's use that. We have all those things you can set to you. It's public. You can. The student can use it. Okay. Take a look at the poster.
Yeah, I will. Okay.
Thank you.